So what are conservative and non-conservative forces? Well, a conservative force is one that does the same amount of work in moving an object between A and B, irrespective of the path taken. The work done only depends on the beginning and final states. One example is the gravitational force. In lifting a mass through a height h, the work done by the gravitational force is the same whatever the path taken. You can go through path 1, or you can take through path 2 to get through the same height change, or you can go through path 3, which is something like this, to get through the same height change. The work done, or the energy transferred of course, depends only upon the initial and the final heights, the height change, and not on the path taken. Another example of a conservative force is the spring force. The energy in the spring depends only upon the amount that the spring is stretched or compressed. So what is a non-conservative force? Well, the work done by a non-conservative force depends on the path. Friction does more work on an object if we slide a body between 2 points by an indirect path from A to B. So something like this, it travels a much greater distance, a distance greater than the displacement. There is more work done. The longer the path, the more work done by friction. It does not depend on the initial and final positions of the body. Therefore, friction is a non-conservative force. Conservative and non-conservative forces have an impact in the way that we apply the conservation of total mechanical energy. When only conservative forces act, we can say that the total mechanical energy in the beginning is equal to the total mechanical energy in the end. Whereas when non-conservative forces are doing work, then we also need to consider a factor with the non-conservative force. Let us consider a situation where we release an object from rest and it falls through a height h without the action of air resistance or any frictional forces. We can say therefore that the total mechanical energy in the beginning is equal to the total mechanical energy in the end. In the beginning, the kinetic energy is 0, and in the end, the gravitational potential energy is 0. Equating the final and initial kinetic energies, we've got that the gravitational potential energy is equal to the kinetic energy. Furthermore, the masses cancel, and that leaves us with a very nice simple equation that we're able to calculate unknown quantities. In this case, the mass need not have been known. Now let's look at exactly the same example, but with a non-conservative force such as friction or air resistance acting while it's falling. We will see that in this case, we actually do need to know the mass of the body. So in this case, we drop a body from rest, therefore initially the kinetic energy is 0. It falls through a height h, and there are non-conservative forces acting because the air resistance acts through a distance h. So we need to take that into account. The final kinetic energy is unknown, but the final gravitational potential energy is also 0. So making 0 the initial kinetic energy and the final gravitational potential energy, we see that the masses now cannot cancel out because they're not present in every term. In solving this situation, it's important to realize that the force and the distance are in opposite directions, and therefore the work done is negative.